Please welcome Dr. Fran Bagenal.
So, the great thing about Juno is it's launched. On its way, it's going, and it will get there. The other good thing is it'll take a lot less time to get to Jupiter than New Horizons will get to go to Pluto. So just to give you an update on New Horizons, it's more than halfway there. It's past the orbit of Uranus. It'll get there in Bastille Day 2015, and then a year after, Juno will get to Jupiter. Just a 5-year trip. So Juno is launched. We had a fantastic liftoff. I'll show you the movies at the end. Great stuff, and we're on our way, and everything is working well. So I'm going to tell you about this mission, a bit about Jupiter, what we're going to study, why we're going there, and basically how this is really going to help us understand our solar system, and perhaps other solar systems too. So if we look at Jupiter as it was observed by Voyager in 1979, and by Cassini. Cassini is in orbit around Saturn, but it flew past Jupiter on its way, getting a gravity kick like many of our outer solar system missions. And you can see it looks very similar. The differences in color are probably as much due to differences in cameras as it is actually in reality. The Cassini team, Carolyn Porco here in Boulder, had spent a lot of time working with our cameras to get them pretty accurate and true color, whereas in the Voyager era we got a little bit yellow with some of our colors. But you can see the bands and stripes are pretty similar, some differences between these two, but the basic idea is similar, and indeed the Great Red Spot was still there, as it has been for 300 years or so. So if we look at Jupiter and spread it out in longitude, you can get to see these belts and zones with winds going in different directions, and the different colors of the clouds have to do with different chemical compositions and different altitudes. But you'll see not only is there the great spot, but also these little spots. And if I show you the Cassini movie, when you put this in time-lapse, you'll see that there are these white clouds going this way, the red-orange clouds going the other way, and you can see the great red spot turning around. So these are very dramatic cloud structures, very similar weather patterns from day to day to day. You'll see the same sort of thing, same sort of storms. You know, if you live in this equatorial region, the winds will always be going in the same direction. Okay. So what are we seeing? What are we looking at? Well, we think that there are 3 layers of clouds, and if we look at, this is altitude, and you know, we regard the zero on, it's difficult with a gas planet, we're zero. So what we do for zero altitude is not a sea level, because there isn't a sea, so you can't have a sea level. What we have is, in fact, we take, I'm embarrassed to say this, we take Earth's sea level. Why not? Just because it's convenient. So the 1 bar level is here, and actually it turns out to be a useful point in the atmosphere. It's above the clouds. And so if you go deeper into the planet, you will get into hotter temperatures. It's hot inside Jupiter because of all the energy that it came from formation. And then it's cooler off, higher up, just as it's cooler as you go up in Earth's atmosphere. And then the upper atmosphere is in fact a lot hotter because, as you'll see, many different particles coming in and heating the outer atmosphere, as well as sunlight. So we look at these 3 layers of clouds, and what we see is the top layer is these sort of white, these high altitude clouds, pretty white, which are ammonia. So that's that smelly stuff that you have in cleaning fluid, and that is the highest, coldest temperatures in the atmosphere. We have a middle layer, which is a mixture of ammonia and sulfur giving things that orangey color that you can see it there in the great red spot. And then underneath is a layer which we think is there, but we've not actually seen, which is water clouds, just like the water clouds in Earth's atmosphere. So that's what we think we're seeing when we're looking at these clouds. When we look at the poles, we see those stripes, east and west zones, an atmosphere that's very dominated by rotation. And then if we take the Cassini movie, remember that this was taken from looking at the equator, so the actual poles are not well imaged at all. You see the belts and zones going in different directions. We'll run that movie again, and you can see how the little eddies are going around, and you have alternating belts and zones. So we have some sense of what's going on with the poles, but just a limited viewpoint. So there are changes. Day to day there isn't much, but sort of decade to decade, we see occasionally new spots. This was first detected by some amateur astronomers, I think in the southern hemisphere. And then we used Hubble to go and look at it, and we found there was a new spot. And then New Horizons that flew past Jupiter, also getting a kick on its way out to Pluto, observed that new spot as well. So there are some changes, but the real issue is what's underneath those clouds, right? So we know there's the ammonia hydrosulfate, but what's underneath? Is there really a water cloud inside? What's the chemistry? What is this big planet, the biggest planet in the solar system, 320 times the mass of the Earth? What is it like inside? And so the Galileo mission sent a probe into Jupiter's atmosphere, and so it had a probe that's sort of about this size with about half a dozen instruments on it and a parachute, and it went in through the atmosphere and then made measurements of the clouds and the composition and so on. And what we expected to see was what I told you, this high cloud of ammonia, a middle cloud, which is the orangey cloud, and then we expected it to go down through the water cloud below. That's what we expected. But what we saw were just 3 puny little clouds, not many clouds at all, and no water. So what happened to the water? Where is the water? And why does water matter? Well, it turns out that what happened was, if we, at the same time that Galileo was going into this region, and it went in between one of these orangey clouds and the white clouds, in through that sort of grey, dark region in there, and at the same time, some astronomers were on Hawaii looking in the infrared at that same region of Jupiter, and you'll see that it glows very bright in infrared, and this tells us that it's a hot spot. And this is a region of hot gas, dry gas, and it turns out that this is where, just like the Chinooks we have here, those warm, dry winds coming off the mountains into Boulder, warming things up very quickly, that's the same sort of thing. It's a down-welling region where dry gas is going down. So it could be that there is plenty of water on Jupiter, we just happen to go into the wrong spot. Okay. So what we found when we went in there is that if we look at the various chemicals that were there, these are the atoms: helium, neon, argon, krypton, xenon. These ones are all inert gases. And then we have carbon, nitrogen, oxygen, and sulfur. Okay? And these ones, carbon, nitrogen, oxygen, sulfur, are quite common gas atoms, elements. And what we find is that most of these things are all about 3 times the amount that you would get in the sun. We know the amount of composition of the sun, and we would think that the solar system would be similar to the sun, or if you enhanced it due to, say, maybe having an extra material coming in time of formation, that you would think all of these heavy elements would be enhanced over the same amount. And certainly a very abundant element like oxygen, you would expect to be up here at 3 times solar instead of about half solar. So what happened? Is this that it's completely missing? Is it that it's local weather, or is it a global depletion? So the reason why this is so important is that we're worried about how the solar system was made. And this means thinking a little bit about the periodic table. We have a very simple periodic table in astronomy. Most things are hydrogen. Hydrogen just dominates the whole universe, actually. But then if you add in some helium, a little bit of helium, and then there's this other stuff that makes up rocks, most of what makes us, most of what makes the Earth that we're standing on. But when we're thinking about the formation of the solar system, we're really interested in oxygen, because if you add oxygen to hydrogen, you get water. Okay? And so water is key, because the amount of water is telling us about the amount of oxygen, which which is telling us about this third most abundant element. And so we would expect there to be a fair amount of oxygen. And in particular, our ideas of how the solar system formed are based on an idea, this is a cartoon, not a real movie, of the solar system forming, where you take clouds around a star, a new star, a big dense cloud that spins, goes around, cools off, and eventually condenses out material. And because water, oxygen is so abundant, we would expect water to be abundant, and that we would expect water to condense out to make snowballs, and that those snowballs would bump into each other and make big snowballs. So our idea of how the gas giants formed is that when we have a star in the center, it's hot, we move away from that star, it cools off, makes sense. And at some point, which we call the frost line, similar to when we have rain here in Boulder and you go up the mountains, at some point you hit the snow line and you have snow above. Same sort of thing in this early solar system, where you had snow forming outside, snowballs forming outside the snow line, making big snowballs. And when I say big, I'm talking 15 times the mass of the Earth, so really big snowballs. They begin to pull in hydrogen, gravitationally attract, sucking hydrogen to make our big, giant gas planets. So our idea of how our solar system formed, and we also think basically how other solar systems formed, depends on this idea of water, and depends forming the cause of the giant planets. And so if we don't find water at Jupiter, what the heck's going on? Okay, so these are the questions. Where's the water? How much oxygen is there in the solar system? And how did the giant planets form? And these are the big questions that Juno will address. It will try and work out the origin of what happened, how Jupiter formed, get some sense of the interior structure, whether it has a core, how the density and temperature are distributed inside, what the atmosphere is going on, how much water is in the atmosphere, and so on, circulation. And because we're flying over the poles, we'll also get a sense of how the Aurora is formed as well. So I'll tell you a little bit about each of these and how Juno is going to do this. So Juno is a large spacecraft. This is a human being for scale. So if we were to take one of these solar panels and try and put it in this room, it would be about the height of me with my hands stretched, and it would go all the way across the room and out of the door a little way. Okay? So these are big solar panels, and they were folded up, hinges here on the launch, and that is providing the power that will power us when we're out 5 times the distance that we are now from the sun. So if you go further out, the flux of sun drops as the distance squared, and so we need to have a considerable large area to power our spacecraft. We have an antenna here that sends information back to Earth. We have a magnetometer. We have various particle sensors. The microwave instrument I'll tell you quite a bit about, because that's a particularly novel instrument. And then we have a camera, a tiny little camera, and a UV instrument and an infrared instrument, as well as some antennas here for measuring electric fields. That's what they are built. Okay, so this is our spacecraft, and it will spin as it goes over Jupiter's pole with the big solar panels spinning around like a windmill. So here they are being built, put together down at Lockheed Martin, just south of Denver. Here you see them folded up, the solar panels. Here you see the magnetometer boom on the end of one of those panels. And I'll show you a movie of how the engineers carefully put together this big spacecraft. So we've chosen our orbit very carefully. We want to get close to the planet because we want to measure the gravity very carefully, the gravity of the distribution of mass inside. But it's a dangerous place to go. And it's dangerous because close to Jupiter, these sort of red areas are danger areas. We know this from flying through them with previous spacecraft, and also from the radio emission they produce from the ground. These are areas of trapped energetic electrons, the radiation belts of Jupiter, the Van Allen belts of Jupiter. But unlike the Earth, which are the radiation belts would be out here, they're in very close to the planet. And so we have a difficult time to decide where to go. The radiation belts at Jupiter, as they are at the Earth, but much more so at Jupiter, are very damaging for electronics. You don't want to take your computer and put it into the radiation environment here, just as you wouldn't want a human to be there. I think a human would probably survive, I think it's about 10 minutes in this environment. It's a nasty place to be, and so we're going to choose an orbit that goes over the top, underneath the radiation belts, and over the clouds. So we duck under the radiation belts and skim above the clouds, and then go back out again. This spacecraft also has very carefully protected itself against the radiation belt by making a vault of titanium, and inside that vault we put most of the electronics that we can, the titanium holding off or keeping away and most of the energetic particles. So this is our spacecraft, hexagonal box, platform on one side, platform on the other. The engine, if you like, will go in the middle, and we'll have an antenna on one side. There's the antenna, and then this is the vault that is protecting the electrons. Okay, so what is Juno going to do? Well, first of all, I mentioned the gravity. It's going to fly over the poles, down past the equator, and measure the radiation. We'll measure the radiation, but it will also measure the gravity from the inside. And that'll tell us, is there a core inside, a solid core? What is the distribution of the material inside? So when we think about the interior, what we know that most of Jupiter is hydrogen. It has a density about 1.5 times that of water, and the outer layers are just molecular hydrogen. But once you go deeper and you increase the pressure in hydrogen, the hydrogen becomes metallic. It becomes electrically conducting. And this is where the magnetic field is. So it's a large fraction of the whole planet is this electrically conducting metallic hydrogen region where the dynamo drives a very strong magnetic field. Now, we think that there may be an inner core of ice and rock. That's the stuff onto which the hydrogen is pulled in the formation of the planet. And then we think at the top, there is probably a region of convection, where water clouds are turned around, but we don't really know how deep that is or how active it is. So we're going to put the spacecraft into orbit around Jupiter, and we will time things so that each time we go by, we go at a slightly different longitude. So we will be mapping out the planet, measuring the magnetic field, measuring the gravity field, measuring the water in the clouds, and then we'll go past, we hope, for 30 or so orbits before the radiation gets to be too much. So that's the plan, and how we measure the gravity is very clever. The spacecraft goes by Jupiter and it sends a radio signal, so think of that as being the blue signal that's sent by the spacecraft back to Earth. And then very cleverly, if there's a deviation of that spacecraft motion due to the distribution of mass inside, causes the spacecraft to wiggle just a little bit, there'll be an offset in that Doppler shifted signal that gets back to the Earth. By measuring that Doppler shift of the radio signal coming back to the Earth, we can measure the small perturbations in the spacecraft position that is due to the interior gravity of Jupiter. This is similar to experiments that are done on Earth, the GRACE mission that has 2 satellites measuring the Earth's gravity very well, or GRAIL, a recent mission that's just arrived at the moon and doing similar sort of gravity sampling of the moon right now. So this will tell us the gravity measurements. The second thing we'll do is measure the magnetic field. We have a sense that the dynamo region inside has motions that turn over this metallic material and generate a very strong magnetic field. And we think that the motions inside are heavily dominated by rotation, producing these columns around, these cylindrical columns inside. That's the idea. What we think is happening, we don't know. So we have a magnetometer. In fact, we have two magnetometers, onboard and outboard magnetometers, and they will measure very sensitively the magnetic field of Jupiter. Okay, so now we want to know what's going on in the atmosphere, and as I said, water is key. And what we're going to do is a very clever experiment where we're going to use the heat that we know is generated inside. Heat of formation, heat of differentiation comes from the formation of the planet. Jupiter emits about 2.5 times the amount of heat that's generated inside than it receives from the sun. So this really is hot inside. It's like a big hot potato that has retained its heat, taking a long time to cool off. So there's heat inside, but you all know that heat coming out as infrared or microwave energy. Now, microwaves, you know that microwaves going through water are absorbed. And you know this because you use a microwave oven to heat your cup of tea. You put your cup of tea in the microwave oven, the microwaves go through the water absorbs those microwaves and heats up, okay? What's happening, we think, here is the heat from the inside comes out as microwaves. Those microwaves go through layers of water, layers of ammonia, different layers of clouds, and will be absorbed different amounts at different wavelengths. So we have 6 different wavelengths of microwaves, short wavelengths to long, between 1.5 centimeters and 50 centimeters. So wavelengths between here and here, and we'll measure the amount of the light, that microwave light coming out. So we have 3 antennas. There's 6 different microwave antennas. This is the big one that measures the longest wavelengths. On the side, and as the spacecraft spins and goes over the planet, it will measure the amount of heat at these different wavelengths coming from the interior. So we expect the longer wavelengths to come from the deepest, lighter ones are coming from above. But we won't just make one measurement like Galileo that went in one place and said, nope, there's no water. We will map the amount of water. So this is an idea of what we think, the colors representing different amounts of water at different altitudes. We expect as we go over to map out the amount of water that's in the clouds and that's inside the planet. So this technique not only just sort of makes a one-spot measurement like Galileo's probe did, we will be mapping out the amount of water and work out both the amount that's there that is important for our ideas of formation of the planet, but also tell us about the meteorology, about the clouds, about the atmosphere, and how that works inside. So it'll tell us what we think it's like inside. We'll use these different methods of probing the interior, and we want to know, is the dynamics inside cylindrical motions like this, or is it more turbulent motions like this? And then deep down inside, we don't want to know, is there a core of metal and water, or is that material mixed in with the material around it? Now we'll also fly over the poles, and that's an advantage for people like me who are interested in the magnetic field of the planet and the very strong influence that has on its environment. The magnetosphere, the sphere of influence of that magnetic field, is huge. So if we took all of the magnetosphere of the Earth that extends out towards the sun about 10 times the radius of the Earth, we could fit that whole thing inside the planet Jupiter. Jupiter's magnetosphere then extends for 100 times its radius in the direction of the sun. So it's a vast volume. It's actually about 1,000 times the volume of the sun and extends out to the orbit of Saturn behind. this vast region is full of a lot of material that comes from the moon Io, and it fills out this large volume. So think about it this way. Here we are. This is actually Utah, but you could be in Colorado. And you put your hand up to the sky, and you will see that the moon, which is just past full, right? So it'll probably be somewhere up there right now. You put your hand up, and you'll see that the moon is about half the width of your extended fingers. If you look at Jupiter, if you could see with magnetic eyes that could see magnetic fields, you would see a region up in the sky that's about 1.5 times the size of your finger, remembering that this thing is 5 times the distance between the Earth and the Sun away, and you would see this big volume of material, of particles trapped in the magnetic field on Jupiter. There's also a very strong aurora. This is gives you a sense of the aurora on the planet. It's a composite that's made. But let me just show you the raw data, because these are kind of cool. These are Hubble pictures taking the ultraviolet of the aurora, and it's going to switch between northern hemisphere and southern hemisphere, but you'll get the idea. We have a large region here, the main auroral oval, and then you'll see little trails or spots around the side. Well, unlike the aurora at Earth, that is heavily influenced by the interaction of the Earth's magnetic field with the material coming from the Sun, all of this is triggered, or most of this is triggered by the interaction of the material coming from Io, that pesky little moon covered with volcanoes spewing off gases. You ionize those gases, they get trapped in the magnetic field, and the currents associated with that plasma coming from Io drive the strong auroral emissions that we see in the polar regions. Now, you will sometimes see something like this, a trail around or a spot. Those spots and trails are produced by a moon. The moons Io, Europa, and Ganymede all produce spots in the aurora because of the currents, electrical currents that flow between these moons and the gases surrounding them and the planet. So you have electrical currents flowing along that excite these very strong emissions in the auroral regions of Jupiter. So this is completely different from the phenomenon we have at Earth. Our moon doesn't produce anything out of this at all. So we'll fly over the poles, we'll duck under the radiation belts, but we'll measure those strong electrical currents that flow between the magnetosphere and the planet, the waves that wheel around and excite the particles, and we'll try and understand what's the physical process that produces this aurora and how that energy has come from the planet and excites these emissions in the atmosphere. We'll, on the spacecraft, there are radio waves that are emitted by the aurora. We've seen this with previous spacecraft, but Juno will have antennas that will go right over the poles and be able to measure in great detail the radio emissions that come from the polar regions of Jupiter. There is a little camera. It's it's an education public outreach camera, and we'll be taking pictures of the polar regions. For the few orbits, it'll probably get zapped with the radiation and won't survive all of the orbits, but we will take some snapshots of the polar regions and the clouds as we go by. And in fact, the decision about where we look and what pictures we take and what pictures we send back will be decided by you, the public. You can go into the Juno website, it's not up yet, but when it's up, and decide, we want to take this one, or that one, that one, and school kids will get involved in this process too. So it's a public outreach activity rather than a science activity. Okay, so let's talk about the spacecraft. I was very lucky to go down, and they dressed me up in the bunny suit, and carefully, there was someone standing on my elbow, all the time, and there was no way I was going to touch anything. I am not an instrumentalist by any stretch of the imagination, so I just looked at it and enjoyed watching this thing being built. And I'm going to show you now a little time lapse actually goes on for several minutes. We'll let it run for a little while, of the engineers putting this thing together. And I think it was probably taken about every 5 minutes or so, maybe not quite so frequent, but you can see the engineers here are dressed up like this to basically keep the entire environment very clean. This material, the air around here is filtered strongly and circulated through. I think they went off on this was maybe Thanksgiving where they were all off. It's a bit of a break, but they come back and then they have tea breaks and then they come back again. But has to be a very clean environment because you don't want to have a lot of dust on the spacecraft. You don't want grease from people's greasy fingers and so on and so forth. And we have a clean room, not as big as this one, which is down in Lockheed Martin, but if you take a tour maybe afterwards or walk around, you will see that we have a clean room with a similar sort of environment where the engineers have to dress up in these suits to try and keep the environment very clean for instruments that are going to go out into space, primarily because you don't want any contamination, but you also don't want any electrical charges associated with dusty dust being deposited on surfaces. So here they are. I mean, you know, they talk a bit, they go and twiddle a bit, come back a bit, twiddle a bit, screw things on, take them off, put them back on again, test them, put them back again, and so on and so forth. Rotate the spacecraft a little bit. The instruments are going to be around the sides here. The vault goes on here, and they took, you know, a couple of years to put this thing together. It's a big spacecraft, but very complicated, and we want it to last for a long time. So eventually, it was put together. Here are the solar panels folded up. It was put into the fairing. Here you are, the antennas here folded up, spacecraft, the fairing at the top wrapped around, and it was shipped over to Cape Kennedy and put on the top of the Atlas V rocket with the solid rocket down here and liquid up here. There it is right up on the top, Juno logo and NASA, all this sort of stuff. And then we went out there, and this is the day before August 4th, the whole science team. This is Scott Bolton, who's from Southwest Research in San Antonio. And after many years, and I would say I started working on Juno probably about 15 years ago, writing proposals, describing what we want to do, why we want to do it, and a lot of engineers working on designing it, putting it together. We were ready for launch, and we actually launched pretty much on time. Rollout is speeded up. It went very slowly out from the fabrication out from the launch pad.
Status check. Go Atlas. Go Centaur.
T-minus 10. 5, 4, 3, 2, 1. Ignition. And liftoff of Atlas V with Juno on a trek to Jupiter. Planetary piece of the puzzle from the beginning of our solar system.
Once you light those rockets, it's not coming back. Now this is looking down. We have cameras on it looking down. We'll come back, you'll see it. Solid rockets here, burning away like crazy. Check this out. You can see the cake, you see that. And there's one.
2, 3, 4, 5,
5 of them jettisons. So now we have the main engines there. You see the darkness and the limb there. And then eventually it's up in space.
Current altitude is 45.8 miles. altitude, downrange distance 69 miles, velocity 5,413 miles per hour.
5,000 miles an hour. Okay? So those bits coming off are just frost. And then you can see it's turning around now. This is the darkness of space.
Full thrust on arrow.
Planet.
Send our closed loop steering as been enabled.
Eventually jettisons the main engine and gets ready for its escape from Earth orbit. So that didn't take very long, just a few minutes in fact, and then eventually the second upper stage got it away from the Earth and it's heading off. It will take 5 years to get to Jupiter. It's in fact on its way out. We'll do a deep space maneuver in September of this year, and then it'll come back and rendezvous with the Earth, go past the Earth, get a gravity kick from the Earth to help it climb out of the gravity well of the Sun on its way to Jupiter. And then it will, of course, we designed it so that it will arrive just as to rendezvous with Jupiter, and that'll happen in August of 2016, so a year after the New Horizons flies past Pluto. So then when we get to Jupiter, I'll just move ahead to that, we'll go into a foreign engine close to Jupiter and then go into very large orbit that then we turn into these close orbits in here. And what happens is that because Jupiter isn't perfectly round but sort of fatter at the equator, the orbits precess vertically, and so after about 20 orbits here, you can see we're now tilted quite far down, and eventually what that'll do is it'll bring the spacecraft into that deadly radiation zone close to the planet. We can't stop this from happening. This will happen not without big engines, and so we expect by about 34 orbits or so, we will actually send it into the planet Jupiter. It's also actually when the money runs out, so if we're still looking healthy, you know, by about orbit 15, we may say, NASA, can we please have a bit more money? You know, missions to do this. Maybe they'll keep it going. We'll see. That's the hope. So Juno will get there, it'll go into orbit, it'll measure the magnetic field, we'll get a sense of the charged particles, the processes that generate the Aurora. We'll probe the deep interior by using gravity, magnetic fields, and the microwaves that come from the inside. We'll try and get a sense of the deep structure inside, and we'll try and work out whether it has a core and where's the water. And are our ideas about the formation of this big giant planet right? Or do we have to go back to the drawing board and come up with different ways of making giant planets? So that's the plan. If you are interested in following, we have a website with a whole bunch of information. It's actually a very flashy website run by Radical Media with lots of interviews and so on and so forth, this one here. And we don't forget July 2016. And in the meantime, if you're following missions and you're interested in little Pluto, we're trying to get a campaign to make a new Pluto stamp. The original Pluto stamp that was put out was 29 cents, which gives you a sense of how long ago that was. We want a new one, so go sign up for the petition. Thank you very much.